Oh, hey, Elliot.
Hey Tom, how you doing?
Hey, can you let me share my screen for a minute?
Yeah, sure.
Okay.
Um, okay,
Okay. Thanks.
sure. Can you hear me okay with this headset on?
Yeah, I can hear you fine.
Okay,
How about
great.
you? Okay.
Yeah, you're good.
Good.
You both sound fine. Yeah.
Great.
Terrific.
Thanks.
Thanks. Yeah, it looks like it's just fired up recording here, so that's good. Used to be a perennial problem last year. I'd forget to start recording, so this is. Right. Oh yeah, you see this polling button is on this Zoom, and it isn't on the Zoom that I use when I just fire up my normal Zoom app.
Okay.
So
Cool. Oh,
that's what the mystery was. Okay. Looks like it's here. I sent you a set of links to YouTube recordings of the videos that were edited for the first 2 weeks of the course.
okay. So do you want to put those on the playlist then, and then add
Yeah,
the lecture from today then? Okay, I'll put those on the
yeah.
playlist.
I think they should go
Yeah.
up on the playlist.
Okay.
The one issue is that on the PDF or the slides for the
Mm-hmm.
lectures, on the first slide, on the title slide, I have a link to the precise place at YouTube where it is, which I'm
Yeah.
assuming doesn't change, right? It's
No, that should be
yeah,
just, yeah, the playlist is just like a link to your link.
right.
So
Okay,
it
great,
should be fine. Yeah.
perfect.
Looks like we got 23, so maybe wait another minute or two.
Sure.
Yeah.
As a little bit of a YouTuber, yes, I can confirm that whoever also confirmed that is correct. The
Okay.
link should be permanent unless you delete the playlist, but I assume you're
Great.
not going to do that.
Yeah. Okay. Perfect.
Great. Thanks. That's very helpful.
All right. I'm gonna. Yeah. At the bottom of your screen, Tom, do you see a polling button? On the
Um,
bottom of your Zoom, like my Zoom controlling bar at the bottom is amplified compared to what it used to be.
yeah,
It has
I think,
polling, breakout room,
yeah.
all this
Well, you're
stuff.
the host for this one, so I don't see that. So I think you have
Okay,
more controls than I do.
okay.
Um, um, okay. Well, maybe it's a good time to get started then. So everyone, welcome to Bioengineering 280A, Principles of Biomedical Imaging. I'm Tom Liu, one of your instructors, and Professor Elliot McVeigh is the other instructor for this course. So welcome. This is our first time doing it all virtual, so bear with us as we sort of figure out different ways of offering the course material in a virtual fashion. So what I thought I'd do is I'd spend the first next maybe 5 or 10 minutes just going over the course information. So if you have questions, you can either chime in through audio, or if you want to post a question versus chat, we will sort of monitor the chat and answer questions that way as well. Okay. So the course description is basically here, and the main thing is we are going to cover X-rays, computed tomography, and MRI in this course. Other modalities will be covered in the follow-up course, Bioengineering 280B, which is offered in the winter quarter. So if you're interested in those, you can take that follow-on course. Because we know a lot of you have different backgrounds, we will sort of spend some time trying to show how the principles of Fourier transform and linear systems are used across the board in all imaging modalities. And so that's going to be a big part of the course. Our contact information here, the best way is probably just email, given that everyone's virtual these days. We have two great TAs for the course, Amanda Crane and Vinay Jani, who also took this course previously as graduate students. So their contact information is here. And you should have received a poll through the announcements asking for your feedback. So once we get feedback on that, they will be posting their TA office hours. So the lectures, you're here now. So they are online via Zoom. And for instructor office hours, we will just stay on the line after the Zoom session for about another hour to have our instructor office hours. And if you need to, if you, for some reason that time doesn't work out for you, just contact one of us. We can always meet, set up other times to meet as needed. Okay. In terms of Zoom logistics, because we're on different domains, I'm in health sciences domain, Elliot's got his through the general campus, we can't sort of easily co-host. So the basic outline is there'll be one Zoom link for the first part of the class, lectures 1 through 9, and Project 1 presentations that Elliot will host. And then we'll switch over to the Zoom link 2 for the lectures I'll give in the second half of the class. Also, an exception is I'll also be giving some supplementary sessions, which we'll talk about in a minute, in the weeks 2 and 3, and those will also be using this second link, and also Project 2 presentations. So we'll send out announcements just when, when it's a separate Zoom link, just to keep you in mind. But if you go onto one of these links and there's no one on, then just try the other link. We will be posting all the Zoom recordings to the YouTube channel. So if you miss a class, you can always catch up by going to the YouTube channel. Any questions up to now? Let me just see, I don't see any questions. Okay. So the supplementary sessions, these are optional, and these are basically because sometimes there are certain students who have a lot of background in linear systems and Fourier transforms, others not so much. And so to help everyone get up to the same sort of playing field, we do offer some supplementary sessions. And so we'll announce those ahead of time. They're on the calendar, and they're right now scheduled for weeks 2 and 3. As we get closer to each supplementary session, we'll be sending out announcements about how to prepare for those, okay? These are completely optional, so it's really meant to help you. It's not, you don't have to feel compelled to go to these if you feel very comfortable with this background. And the recordings will also be posted, so you can always look at them online if you miss one and want to catch up on the material. Okay, so the required text, we will be using medical imaging signals and systems. You should be able to access that through the Red Shelf module under the modules folder. If you have any issues, let us know. There are mistakes, so you want to check out this errata in case, for example, you're doing an assignment or a problem set and something doesn't seem right. There are corrections listed here. There are other supplementary texts. This is just one of them we listed. In the past, we used to put these on course reserve, but because the library doesn't have any physical reserves now, it's they're not on reserve. But this is a fairly inexpensive set of notes from Dwight Nishimer at Stanford that some of you might find useful. The course materials, all through Canvas. We'll look at the module section in a bit, but all the lecture slides will be posted there. In addition, if you want to look at stuff when you're doing projects and things, you can access previous courses here and supplementary videos here, and all the recordings from the past 2 years are on our YouTube channel here. For grading, we're going to have, potentially throughout the course, there'll be online quizzes and surveys. These will be really just sort of participation. That don't worry about whether you get the answers right or wrong. It's really just, are you sort of to help sort of keep things sort of lively, and potentially we may use breakout rooms for those as well. There will be homeworks, probably about 7 or 8 homework assignments, and those account for 15% of your grade. The online participation is 5%. For the projects, in past years, we've had exams. So because we've gone to virtual this year, we've decided that it's probably best just to have projects. So we're going to have 2 projects, each worth 40%. And the way these projects will work is project 1 presentations will be held over 2 days during the quarter, and we'll go over that in the syllabus in a minute. And the project 2 presentations will occur during the final exam slot in lieu of final exam. So there'll be no final exam for this course. There will be no actually exams at all for this course, aside from the projects, okay? Class participation, we will use Canvas Assessed Learning, and we'll talk about that as we have the surveys. One additional note is we will, especially since we're more project driven this quarter, there will be quite a lot of use of MATLAB. You'll be exposed to that in both the homework assignments and some of the project assignments. We know that some of you have a lot of experience in MATLAB and others don't. So the TAs are going to be offering some tutorial sessions on MATLAB to help those of you who are need a little help in that area. Okay, so if you're interested in having a say in when the TAs have their office hours, or interested in the MATLAB sessions, please respond to the poll that's in the announcements, and so that can help the TAs prepare. So let me just go over really quickly the syllabus. So this is all tied to your calendar as well. So you can sort of see we have the weekly lectures. We have some supplementary sessions scheduled here. These are on schedule right now for Fridays at 10:30 to noon. I will send out a poll probably through Canvas, just sort of seeing what times work out best for people. And then the other thing I want to point out is the project 1 presentations are here the week of November 16th. So that is the week after the Veterans Day holiday. And then the project 2 presentations are here. That's during the final exam period. So that's a 3-hour period. So we'll talk more about the projects as the quarter continues. Let's just look really quickly at the modules. So if you look at the modules, here's the red shelf module for your textbook. Here are the slides. The ones that have 20 have been updated for this year, and as placeholders, we've left in the ones from 2019 just to remind ourselves of what we had last year, but you're not responsible for anything that has 2019. It gives you a sense of where we're going, but the main thing is the ones that we'll be using are the ones that have 2020 on them. The other thing that you may find helpful, although maybe not so much this year, is we do have all the quizzes and quiz solutions from previous years. There's no quizzes this year, but if you just want to see what they look like, they are there for you to look at. Okay, so that's all I really had to say. So are there any questions before we start the lectures with Dr. McVeigh? Okay, great. So I'll stop sharing my screen and turn it over to you, Elliot. Okay.
Great, thanks, Tom, for the overview there. I'm going to share my whole desktop here. So today, what I'll do is I'll give the first lecture, we'll do it entirely live. However, as we move forward, I think one sort of optimal way to do this course would be if you were to watch the lecture ahead of time, and say in the first half of the assigned lecture time, which would be from 11 a.m. to 11:40. And you can watch one of these lectures. They're all on YouTube. You can watch one of these lectures in 40 minutes if you watch it in 1.5 time. And that sounds like it might go a little too fast, but it certainly doesn't. Actually, if you watch something in 1.5 time for a good 20 minutes or so, and you go back to normal time, the person sounds particularly drowsy and maybe even a little tipsy, right? So you get used to life in 1.5 time when you watch YouTube videos in 1.5. But today we'll do this lecture in its entirety live. When we come in, say, we'll try this on Wednesday. When we come in at 11:40, then instead of me going through the entire lecture, I can hit some high points of things that we really need to know. We can start with a short quiz just to make sure that like if we organize it as a poll, then I'll be able to tell whether or not people understand what's going on, or if there's a big gaps somewhere. And then we can do some high points in the lecture, and we can do some examples that will lead into the problem set, right? So that you have an idea of how to address the problems on the problem set. And I think that should be a pretty good way to organize it. So 40 minutes of viewing the video. I don't expect you to watch that video outside of the lecture time. You can complete it inside the lecture time if you do 1.5 times, right? Because a lot of them are like an hour, maybe an hour and 10 minutes or something. Ideally, as questions arise, it would be great if you emailed them, or when we get it to the session, we put them in the messages so that we can keep track of those questions and get them all answered. Okay. Okay, let's go back to here. So we're gonna start this up. Are there any questions thus far on that? Can everybody, well, if you can't see my screen, it would be great if you gave me some indication that you cannot, or if you can't hear my voice, although you wouldn't have lasted this long probably.
Screen and voice seem fine.
Great, thanks. Okay, we've got two parts to this. We're going to look at the overview of imaging modalities, medical imaging modalities, not all imaging. And we'll do a quick introduction to image quality, hopefully, if we get there. Both of these lectures from last year are at this location on YouTube, and they're open to the public, so you should be able to see them. So ideally, at the end of this course, you should be pretty confident in your understanding of at least two major modalities, which is computed tomography and MRI. And that makes up a fairly significant fraction of the medical images that are obtained, at least in the United States, each year. With that understanding of how you make the picture, how you evaluate whether or not the picture is any good. So signal to noise ratio, contrast to noise ratio, what is spatial resolution? What can I resolve in this picture? What can I expect to be able to diagnose from this picture? We'll look at some current applications towards the end of each section. And ideally, at the end of this, when you look at a picture, look at an MR image, say, or a CT image, you should be able to figure out what is actual signal, what is artifact, what can I believe in this picture, what do I have to look at with a grain of salt because I don't think that's actually happening. And then ideally you'd be able to show with mathematical rigor why something is the way it is. So here's the basic process of how medical imaging is done. You have a patient with different anatomical parts. The imaging device derives a signal from the patient. That signal we'll call the measured data or the raw data. And then usually there's a reconstruction algorithm that's applied to this raw data in order to present a representation of the patient. And remember, it's not an actual photograph of the patient in the sense that the reflection of light from a section of the patient, as this is trying to emulate, but it is a representation of the patient in terms of brightness is different for different tissues. The first medical imaging was done with X-rays, and it was done a couple of years after X-rays were discovered, right? I think the first X-ray imaging devices were maybe 2 years after Röntgen discovered X-rays, and then the first field medical X-rays were done in World War I. They had these, Marie Curie and her daughter actually went out into the field with trucks with X-ray scanners in them, if you can imagine that. Point of fact is that Marie Curie won a Nobel Prize and her daughter won a Nobel Prize. not well known though. Bloch and Purcell, they discovered nuclear magnetic resonance independently on each coast, one at Harvard, one at Stanford. And that would become the signal that is used to make MRI imaging about the same time as Hounsfield is developing CT scanners using X-rays. Paul Lauterer is developing an MRI scanner, or a way to measure spatial position of things with MRI. Let's see if I can get a laser here. There we go. And the CT scanner preceded the MRI scanner by about, the whole body CT scanner by about a decade or 8 years or something like that, which doesn't seem like a lot right now. This is an X-ray image of Dr. Runken's wife's hand, right? And this is a ring, which is attenuating the X-rays much more readily than the bones in her fingers. And so it doesn't take long before, when something's discovered, to turn it into a medical application. The basic geometry of how this works, or how X-ray imaging works, is you have a source of X-rays. It's like an X-ray light bulb. It's called an X-ray tube. And those X-rays emanate from that tube, ideally from a single point. However, there's obviously a certain area over which those X-rays come from. They fly towards the patient. Some of those X-rays are absorbed by the patient, and some go straight through. The ones that go straight through hit a detector. In this case, let's say a film screen system. When they hit the detector, for a film screen system, they give off a bit of light. They expose the film, and you get a negative image of the patient. That's a traditional chest X-ray. CT is virtually the same. It's just you take many of these pictures from different angles. Here's a very early X-ray system where we have the X-ray source here. This is a voltage generator to accelerate electrons to a target such that you make X-rays and they come spraying out of here. This is the patient who's having their chest X-rayed, obviously, and they are holding the detector. They're holding the film screen detector as close as possible to their chest. Don't have to do that anymore. Now in a modern system, you lie on a table, a X-ray source is placed in front of you and a detector behind you, and the image is taken. And this poor devil is going to drink some contrast agent to highlight the differences between his esophagus and the background. X-rays were not always used wisely. This is in the 1930s. A number of companies introduced machines that went into shoe stores in which you placed your feet on a platform, and then an X-ray source shot X-rays through your feet, and you got to look at your toes to make sure that they had enough room and you were quite comfortable. Needless to say, once it was discovered that X-rays cause double-strand breaks in DNA and that too much X-ray is not a good thing, these machines were discontinued. Millions upon millions of these images are taken each year and across the world, and this is a simple projection of the patient in an X-ray image. This cloudy signal here shows the inflammation of the lung tissue, so that there's less air and more fluid in this section of the lung, showing pneumonia. And it's a very, tried and true way of detecting pneumonia in patients for a very small X-ray dose and very quickly and very cheaply. You can see also there's the outline of some structure here. This inside this sac, that is the heart, and then this is the spine, and the ribs are quite obvious here. This is a mammogram, it's called, and it's an X-ray image of a female breast. This is used to detect cancerous lesions in the breast tissue. When you look at, this is a traditional 2D mammogram in which the breast is compressed on a plate, an X-ray source above the plate, transmits X-rays through the breast, and the detector is below it. This is a three-dimensional image. It's a 2D projection through a three-dimensional image made with X-rays. It's called tomosynthesis. It's like CT for the breast. And the claim is that you can detect this lesion much more readily than you can on the two-dimensional image because of the interfering overlying structures. It also doesn't hurt that there is a very large white circle around the lesion. To point it out, if you put the very large white circle around this, you'd probably think that was the lesion as well. So there's a little bit of uncertainty as to whether or not this is a lesion. This is a very difficult imaging modality to read. A human being needs a lot of experience to read these well, 2D mammograms, and it's one of the primary applications for artificial intelligence, for example, to scan these images to learn from the clinical outcomes data which are the positive scans and which are the negative scans, because it's very subtle, the signs and the textures and structures inside these pictures. But this picture, the basic contrast comes from differential absorption of X-rays that are passed through the breast. You know, the one problem about doing this is I cannot see the chat box. No, that's not it. Okay. Okay, this is a X-ray image. It's a single frame from a movie. And this movie is obtained by continuously irradiating the patient with X-rays while you inject contrast agent down into a vascular structure. In this case, this catheter has been plugged into the root of the coronary artery in this patient, the left main coronary artery. And during that injection, the X-rays are turned on and the sequence of images is obtained. Usually about 15 images per second, sometimes 30, depending on the needs of the clinician. This imaging modality is the standard way to detect a lesion or a stenosis, a narrowing of a coronary artery, which is a precursor often to a heart attack. And so this signal up here, as you see, the vessel gets larger here, and it looks a little bit dim and narrow right here. That is a lesion in the, probably what is the, it looks like the circumflex artery going around the back of the heart. So getting to this position where you lie down on a table and have this basically catheterization done and fluoroscopy images taken in real time, usually you need symptoms. And you come in with chest pain and they take you to this scanner and take these images. It's not inexpensive because you have a lot of highly trained people doing this procedure in real time. But it is considered the gold standard for determining whether or not your coronaries are open or closed. Computed tomography has a long history. First, the radon transform was established mathematically for actually understanding what a two-dimensional object is just from the projections through the object. This was adapted, the radon transform was adapted to X-ray imaging by Alan Cormack, and Hounsfield built the first CT scanner at EMI in the 70s. And it's a fairly simple principle as to how this works. If I have an object and say this object is this circle with these smaller ellipses inside, and I essentially put an X-ray beam through that object and measure how many X-rays come out the back. When I have something that absorbs more X-rays, I will see a drop in the number of X-rays in my detector below that object. This is a thicker object, and so when I look down here, I see a larger drop in the X-rays that are coming through the object. So just from this single view, right, here, along this one-dimensional projection of this object, I can tell you, well, there seems to be at least one major X-ray absorber somewhere in this column, and another major X-ray absorber somewhere in this column. I don't have any information as to where it is up and down in this direction. I just know it's in there. So when you back project So if you just take this function and plot it at each location along here, as I back project this one-dimensional function onto the 2D plane. So I can see I have, if I look and say, well, how much absorption do I have? Here I have no absorption, medium, high absorption. So I plot it so that it goes up, and it goes up higher here. This type of image can be used if we take multiple views from different directions in order to locate where these objects are. So if I take another view this way and I project my X-rays through the object from a different angle, I'm looking at it from this angle, like here I was looking at it top down. If I look this way, then I get a different one-dimensional pattern of absorption. If I back project that one-dimensional pattern of absorption and add those two pictures together, then I get a peak here, which tells me, well, that's a better estimate of where that large X-ray absorber is. And here's this intermediate X-ray absorber. Its location is up here. This is just with two views. It's a very simple object, and so you get this estimate of where those are. That's essentially how computed tomography works. We're going to do, instead of 2 views, we'll do upwards of 800 views, 800 different angles, and get a very high resolution picture. What does the detector look like for X-rays? If we go back to this slide and ask, well, this function here, you know, that it says I have more absorption here and even more absorption here. Who does the counting of those X-rays? What are they hitting? Well, it's an X-ray detector along here, and if our source is coming down with parallel lines like this, we can just count the number of X-rays that hit each cell in this detector, and then we have that one-dimensional function. Oftentimes, CT scans are inside a cylindrical tube, and so the detector is essentially an arc of a circle, and the source, instead of being parallel lines like this, which you have to raster across, hard to engineer that to happen. If we have a single source, we can get these different projections through the object from a single source all at once. So this speeds up the whole process. Obviously, I can just do a flash and I get all of these sources at once. Whereas this, I would have to raster across and get each, each projection one at a time. Modern CT scanners actually have this arc around the circle, and they have many detectors in the Z direction or along the cylinder as well. Some modern scanners have 320 in this direction, some have 256, some have 64, but it has made a huge difference in terms of the time needed to acquire all the data required to make a CT picture. I have an X-ray source that hits every, a ray from the source can be matched to every element in the detector, and so it's just a flash, and I have a two-dimensional picture of the projection of X-rays through that object. So that's the evolution of the detector geometries. This is the way that detector geometry is set up inside a CT scanner. I have a detector organized in this arc here. I have a source up here, and then the beam, it's called a fan beam, gives me projections through my patient who's sitting inside the cylinder in the CT scanner. And then we rotate the position of the source such that we get different views through the patient. Another trick in modern CT scanners is you can continuously rotate this source and detector pair while moving the patient continuously through that beam of X-rays to get a large field of view X-ray image or a volume X-ray image. You can imagine if I have a very thick detector like this, and so I'm getting a very thick amount of data each time, I can move the patient through there very quickly and still achieve all of my data. This is what raw data looks like when it comes from a CT scanner. This is the scanner we have at UCSD, and I just pulled this raw data file and sifted through the data to make these projections. So this is the detector array. It's approximately 1,000 elements in this direction. It's 256 elements in this direction.
And also, you don't need
Just let me,
because the hanger doesn't really fit.
got it.
So can you see?
Okay.
So do you see your times?
So you can see basically the different projections as we rotate the source and the detector through a patient. This is the liver here and the diaphragm. This is the, essentially, I think that, oh, that's me. That's the video itself, somebody's talking. This is the profile of the heart, and you can see some vascular details in the lungs, and you can see a high X-ray attenuation through the spine, which is here, right? It's bright. That's the spine right there. We're looking straight down at the patient. If we look at, say, this orientation, the spine is here, and the heart is here, and then this is the diaphragm.
Pattern.
So 1,000 by 256 seems like a small camera, right? For this day and age, when you look in your phone, most phones now have 3,000 by 4,000 detectors for their photography. So it's a 12 megapixel camera. This is, you know, much smaller than that. However, this is an X-ray camera, so it makes it quite different. And we're going to use all of these projections to create a three-dimensional image of this patient's heart and chest. The quality of X-ray images has increased extraordinarily over the last 30 years, 40 years. Here's an example of, this was a commercial scanner, Siemens scanner imaging the brain in 1975, 128 by 128 pixels, a single 2D image, and that's the quality you get. Now, not bad actually. If somebody had a large hemangioma, or they had some other kind of bleed or something in their brain, you could actually see it with this, whereas on a plain film, you probably would not be able to see it. So it was a huge jump for radiology at the time. But when you compare it to a modern CT image, this is where the image quality is now, sort of a 512 by 512 matrix over maybe a 20 centimeter field of view. And you get extraordinary high resolution details of the brain. This is what a scanner looked like back in the 70s. It hasn't changed a heck of a lot in the sense it's still got a cylindrical structure. The opening is larger, it's more comfortable. Patient table is you know, very functional, and you can move the patient around inside the scanner. Here's the type of image that can be achieved if you essentially push the patient through the scanner in that spiral scan technique. So this person, you know, shows up at the emergency room, acute chest pain. You're trying to figure out what's going on. You just scan, you inject a contrast agent into their vessels and scan them from top to bottom and try and find what is going on. And it turns out that this person has a very serious aortic dissection that could have occurred traumatically, or it could have occurred naturally. But immediately, the team knows what to do, and you're in the right place. This is with the rest of the image removed, showing this aortic dissection. Now, this image in a modern CT scanner would take about 10 seconds to acquire, maybe less, to scan this patient from the top down to the bottom. So it totally revolutionizes what happens to a patient when they walk in the door of the hospital with some kind of acute problem. Just to look at the parameters here, the whole, man, I was way off. The whole scan time is under a second for this, right? The scan length is, you know, 500 half a meter. Rotation time of the gantry is a quarter second. So that means that that gantry with the source and the detector is rotating 4 times a second around the patient. And the total dose that the patient acquires from the x-rays for this exam is 2.7 millisieverts over this part of their body. Just being alive and walking around for 1 year, your estimated dose is 3 millisieverts just from, you know, cosmic rays and natural radiation from radon and things like that. So needless to say, the number of CT scans as a function of time has gone up extraordinarily. And so this is just the number of visits with the CT included to the visit from 1995 till 2007. So it's transformed healthcare in the sense that back in 95, you know, I started medical research back here in like 84, maybe off the page here somewhere. And then as these scanners got better and better, virtually everybody who has a malady is getting a CT scan, such that now you're up at 16 million CT scans a year done in the United States. So it's a fairly significant load in terms of cost and in terms of global radiation dose to the population when you do that many CT scans. And so a number of people have looked at this sort of on an epidemiological level to determine like what is the result of doing this many CT scans. For the patients who need it, the results are fantastic. I mean, you get the right care. You don't go down a blind pathway and get treated for the wrong thing for a long time. So it's terrific. The issue is you want to make sure that the people going into the CT scan are the people that need a CT scan. Right. This is a CT scan of a heart, and you inject contrast agent into the patient before taking the scan such that the vessels inside the patient light up. And you can see this is the aorta of the patient, and this is called the left anterior descending coronary artery. This is the circumflex artery back here. Here we have a branch of the LAD coming down here, another branch. The right coronary artery is going around the back of the heart this way. Extraordinary resolution. No other imaging modality can give you this kind of volume coverage and 3D information in such a short time. I would encourage you to go to these sites. You can pick your company. I'm not endorsing any of these companies, but each company, GE, Toshiba, you know, Hitachi, Siemens, etc. They all have fantastic websites giving example images to give you an idea of what's available and the applications that are available. These are just a few examples, but I really recommend you go and just take a look around the web at those sites. Moving to MR, the NMR as a phenomenon was discovered in the 40s, and this is radio waves emitted from the nucleus. And it turns out if protons are in a magnetic field, they will be sensitive to their spin orientation in that magnetic field such that they will absorb radio waves that take them from, you know, a high state to a low state in terms of their orientation with respect to the magnetic field. This, you'll hear about this more from Dr. Liu, but it gives you the ability to generate a radio frequency signal from a patient, from principally all the water in the patient. It's all the hydrogens in the patient. It's, you know, so some are in fat molecules and mostly in water. Paul Lauterbur published the first NMR images in Nature back in the 70s, showing just 2 blobs where he had 2 samples in his NMR spectrometer, and by applying magnetic field gradients, he was able to resolve where those samples are. Also, this guy wrote a fantastic electricity and magnetism textbook. I know that because we used it in second year physics. So I recommend this book to anybody who wants to learn something about electricity and magnetism. It's great. Here are some of the early sort of home-built MR images. They were either built with private funding, or in this case, they were built in universities, principally in the United Kingdom, were the first ones. These are the team of folks who built these scanners. And you can see these windings here are a static magnetic field. This is a radio frequency coil. And then there's a lot of electronics to drive both the radio frequency coil and transmit and receive with the radio frequency coil, and then push current through these gradient coils to change the magnetic field. A modern MR scanner that has a very large magnetic field is shown here, say a 7 Tesla magnetic field. And you have many, many windings that are conducting current basically in a bath of helium, so that the wires are superconducting and there's no resistance to the flow of electricity, and you can just generate a huge current in these wires and make a big magnetic field. And then the patient lies in that magnetic field, and you perform radio frequency coil and gradient coil pulsing in order to generate signals from the patient that you can image. As time goes on, these magnets get bigger and bigger. Here's a standard off-the-shelf 3 Tesla magnet that you can buy from virtually any manufacturer. This is a 7 Tesla magnet. This is the head coil here at the University of Minnesota. This is an 11.7 Tesla magnet. And I guess 11.7 is a magic number because there's also an 11.7 in France. And so the push towards higher and higher magnetic fields is to get higher and higher sensitivities to lower and lower concentrations of elements in the patient. So you just get bigger signal as the magnetic field goes up. But other complications abound, not just the size of the darn system. It gets a little out of hand. This you can bring to any clinic on the back of a truck and 3 guys can put it together. It takes a nation, But you can derive absolutely spectacular images of humans from these scanners. This is 3 images of the same brain, same slice, showing the variability in brightness of different tissues in magnetic resonance imaging. This is called a T1 weighted image, where we have dark pixels represent cerebral spinal fluid that has long T1 values, and then these gray pixels are the essentially gray and white matter of the brain. The lighter signal is the gray matter, the white matter, and then the darker signal here is the gray matter. This is the very bright signal here is subcutaneous fat, and the really dark signal here is cortical bone that has very low density of hydrogens, and so basically no signal. This is an image that is purely weighted on the density of protons at each pixel. And this is an image weighted on what's called T2, which is the kind of temporal decay of the signal. When you excite a signal from a patient, it decays away in a few hundred milliseconds usually. And the cerebral spinal fluid takes a long time to decay away. The gray matter takes a shorter time. The white matter here, the connecting tissue in the brain, takes a shorter amount of time to decay away than the gray matter, which is on the outside. Here is a beautiful MRI picture made without contrast media of a human brain. And so these are the vessels, blood vessels in the human brain. So you get a very nice picture without injecting a contrast agent. These images are proportional to the amount of blood flow that is occurring at each region in the brain. So these images are anatomical pictures, and then the associated blood flow is shown in these images through a technique called spin labeling. And we have some of the world experts on this type of imaging here at UCSD. So if you're interested in that, there's plenty of people to talk to about this. MR imaging of the heart can be achieved by gating your image acquisition to the patient's EKG. And you assume that the heart goes back to the same position periodically with the EKG waveform, and create a set of images across the R to R interval between the EKG. And then when you play those images back as a movie, you can essentially see a movie of cardiac function. This bright signal is blood in the chamber. This is myocardium or muscle. So you can measure how the muscle is contracting and whether or not this patient has normal muscle contraction in their heart. If they do not, that's a really strong sign that they have some kind of ischemia or other problem with their heart. This is very bright signal from the fat, subcutaneous fat of the patient. This is the liver in this patient, and a very bright signal in the major vessels in the liver. And looking, the other advantage of an imaging technique like MR is that you can image the heart at different orientations. And so here, this is the valve plane of the heart here. The chamber, the left ventricle and the right ventricle are here, and the blood is being ejected out of those chambers on each beat. This is the same beat played over and over, and these images are obtained by compiling signal over sometimes 6 beats, sometimes 12 beats. But you can see during that time, the patient has been holding their breath so their chest does not move up and down. And this is called a long axis view of the heart, showing the septum of the left ventricle and the free wall. Another very interesting mode of MR imaging acquisition is called functional MRI. And it turns out that as blood flow changes in the brain, if you activate a certain regional portion of the brain by asking the patient to do a task, such as tapping their finger or thinking about a chest move, the imaging signal will be modified because the blood flow gets modified at that region. And so if you repeat that task over and over, you can see the signal go up when the task is on here, and average that together to get a map of what's called the brain function or functional MRI. And again, UCSD has some of the best people in the world for functional MRI. So if you're interested in this, I advise you to start with Dr. Liu. He can put you in contact with many people who know all the ins and outs of this technique. It's really cool. MRI is also able to look at the motion of water inside cells on a submicroscopic scale or on a microscopic scale. And the way you do that is you measure the diffusion coefficient of the water in each cellular compartment, or in each compartment, or voxel here will say, what is the diffusion of the water in that compartment? And if the diffusion is faster in this direction, if the water is able to move more quickly in this direction, it will attenuate the signal when the gradient is oriented in that direction. And you can measure that by doing different gradient orientations and measure actually a diffusion tensor at each location. From that diffusion tensor at each location, you can then track essentially neuronal tracks through the brain and come up with things that look like this, which is essentially a connectome of the human brain. These are tracks that have been traced using these diffusion tensors through the brain, and showing this basically which areas of the brain are connected to other areas of the brain through these white matter tracks. And so there's been a huge amount of work done in diffusion MRI to do this kind of mapping. Okay, so that's an end to the introduction of the imaging modalities that we're going to be looking at for this year. or this quarter. And now we'll go into a description of image quality, but I want to pause briefly to ask if there are any questions about what we've talked about so far. I haven't really kept my eye on the chat feed because I'm trying to see where it is here.
Like, there was a question about, hey, Elliot, there's a question about whether table speed was ever an issue.
Back. Okay, here we go. Okay, so I think a lot of chat has been going on. Okay. Sorry, I was unable to answer these while we were going. Does anyone want to ask a question live? You can just speak up if you wish. No? Okay, so let me read a few of these questions and then we'll make our way back. Are there any risks associated with undergoing MRIs like radiation is an issue with CT and X-rays? The principal risk of undergoing an MRI is essentially being struck by a flying metal object. So you're in a very high magnetic field, and if there is any object in the room that is ferromagnetic, such as an oxygen bottle or a piece of metal in some medical device, the force on that object is essentially too great for you to hold on to it and stop it, and so it will just fly into the scanner. So that is the principal risk. The other sort of less common risk is if you are in a scanner and the RF energy is being used to a great degree over and over and over, you can heat up. So you warm up a little bit. But normally the scanner has software to protect you from that occurring.
Hey, Elliot, do you mind reiterating the diffusion MRI and what exactly that does?
Okay, so it looks like Tom has been answering the questions. Okay, so we are at 11:55 and we're going to go to 12:20. So that's great. We can pick up on image quality and get to the end of it by today. I wouldn't mind trying a poll at some point to see if it works.
Yeah, can you hear me?
Oh, I see. Maybe everybody's muted. Is that the case? Okay. Thank you very much. Can somebody try and unmute themselves and
Elliot,
ask
can you hear me?
question?
What is it?
How about,
I can hear both of you.
Yeah, we can hear other people talking.
Yeah, Elliot, can you hear us?
Oh, yeah, I can't hear any questions. So
he did turn off all of his audio on his Mac for some sort of video, so it could be that.
And maybe just increase the volume on your Mac.
Someone might have to put that in chat,
this.
though. Sorry about the water sounds.
Sorry, I'm just trying to figure out this mute business here. Okay. So it doesn't seem like I can hear anyone. Siddharth, are you? No, it says you're muted too. Okay, so I'm going to have to figure that out before next time. I'll invite more. That's cool to unmute.
Can you hear me?
Ah. Thank you. So I turned down the volume when the movie was playing because there was a lot of crap on it. So, okay, so now I can hear you. Sorry about that. Okay, any other questions? No, we got that figured out?
There was a question from Alex, I think.
Okay, Alex, you want to shoot?
Hey, Elliot, yeah, a quick question, just a little bit further, if you could elaborate a little bit further on the diffusion MRI. I didn't quite understand. You were saying that there's some sort of, water flow going through the axons and white matter channels.
Right. So the best way to think of this is if you had a celery stalk okay? And you might imagine from its texture that it has a lot of cells that are longitudinal this way and that way, right and left. And so the water, it can flow in that direction more easily than it can perpendicular to that direction. Not only flow, but it can diffuse. So if you put a dye in there, you would see it diffuse out in one dimension along the celery stalk. And so there is a way to measure that diffusion coefficient in all directions with MRI. So if the diffusion coefficient in the XY direction is different than it is in, say, the Z direction, you can see that asymmetry in MRI.
Okay, so you're kind of measuring the mass of the water molecules flowing in a certain direction.
It's actually an interesting thing. It's a random motion of the water molecules, and that random motion it goes on a random walk, and it can walk farther in the direction that it can diffuse longer, right? So what happens is the signal actually decays away more quickly in that direction when you put gradients in that direction. So it gets dephased, it decays. And so you can probe different directions by changing the magnetic field gradient. There's a great paper by Steskel and Tanner, and I can put it up on the Canvas site. At the end of this, I'll put a link up to that paper. Great thing about the Steskel and Tanner paper also is it was like from the 60s, and they did diffusion MR in their NMR spectrometer. And when you write out the equations in the paper and you look at the equation, then the MR imaging equation is essentially in their paper. They just didn't notice. So, and that's from like the mid 60s, right? Any other questions?
Hello, Professor. So I'd like to ask if this course requires prior knowledge of Fourier transform.
Okay.
Yes, I didn't learn that.
Yeah. So we put it this way. If you have experience with the Fourier transform, and you have experience with linear systems or systems and signals from electrical engineering, this course will be kind of a breeze on those topics, right? We do count a lot on the Fourier transform in this course because it's used all through CT and it's used all through MRI. In fact, the imaging equation in MRI that gives you your image from your raw data is a Fourier transform, right? So you really have to know it. You don't have to know it ahead of time. We will do our best to teach the Fourier transform in this course, but it'll take a little extra work and practice to figure it out. Does that answer your question?
Okay, yes, thank you.
Okay.
Questions on chat, Elliot.
I got some more questions here. People who what they prefer in their pronouns. My pronouns are he, him, and you can address me whatever makes you feel comfortable. But my name is Elliot, so you can call me Elliot if you want. Or if you feel uncomfortable doing that, you can call me Dr. McVeigh. Okay.
Yeah, same with me. You can call me Tom, Professor Lou, Dr. Lou, whatever makes you comfortable. And my pronouns are he and him.
And there's another question here. Is there any way for the MRI machine to tell if there's metal in the body and where in the body the metal is before turning the magnet on to get the rest of the image? That's a fantastic question, and shows you're thinking about the process. Like, how do I do that? Early on in MRI, a very dangerous situation was when somebody showed up and they had a surgical clip in their brain, because early on, this is way back in the mid 80s, surgical clips, a number of them were ferromagnetic, right? And so you did not want to go in an MRI machine with a surgical clip in your brain because it would torque from the force from the magnetic field. You did not test it with the MRI scanner. You tested the patient with an X-ray image beforehand. So you take a picture. If there was some history of neurosurgery or some history of any kind of intervention, usually that patient got an X-ray first, and you'd look and see, is there metal in there? Doesn't look like it. We can go ahead with the MR. The difficulty with MR and turning the magnet off and on is that virtually all the systems that are used clinically, except for very few, the magnet stays on all the time. And the reason it stays on all the time is that the current is so huge and the magnetic field is so huge from that current, you get it in this state, and it's a superconducting state. And to ramp it down and ramp it back up takes hours. It doesn't take, like, you don't switch it off and switch it back on. So it's charged the whole time. That's why early on in MRI days, there used to be a metal detector at the door of the MRI scanner. And when you walk through, if you had, say, a spanner, like a wrench, you know, you were someone who was going to fix something, and it was in your pocket, the metal detector would go off until you don't go in there. You've got metal on your body. But the problem was when you turned up the sensitivity of that metal detector high enough such that it got the important stuff, it always went off, like your glasses, the eyelets in your shoes and everything. So the thing was always going off. So something that always goes off is useless, right? So that's not really done anymore. What's done is a pat down. You just make sure you don't go in there with metallic objects. And if you're anywhere near an MR scanner and you're in control, you're a tech, you're a scientist using it for an experiment, everybody else other than the patient, you have training. And the training is like how to make sure no metal goes in that room. It still happens though. Another question is, what is the idle power consumption of an MRI scanner? There is a chiller, which kind of is just like a refrigerator unit. So it's probably the power of a really good refrigerator, like a big freezer. Other than that, there isn't a heck of a lot that the room's air conditioned. Tom, is there any other like baseline power you guys need?
Well, just enough to keep all the electronics on. So, you know, you have a few racks of electronics that's at idle. The real power is when you turn it on, and we'll talk about it more when we talk about the gradients, but that's a tremendous amount of power once we start switching it on and off.
So you said you keep it on, I assume you keep on in terms of like you keep the helium cold and everything. That's what takes hours. Do you then switch on and off the magnets? I assume you don't have the magnets on all the time, or you're not passing current through them all the time?
Yes, you are.
You are, okay.
Once they're superconducting, there's no actual cost to doing that other than maintaining the helium, which boils off. So you've got it in a bath of liquid helium, which is like, what 2.7 Kelvin or something? What is it, Tom? It's, yeah, 2.7 Kelvin. So it's super cold. It's super expensive. It comes in a big vat, and then they pump it into the cryogenic container. And you fill it up, cap it off, and then that boils off over time, and so you have to refill it like once a month or something like that.
Yeah, I mean, what you'll hear is the sound you hear is the pump that tries to take the boiled off helium and recondense it, so you have less boil off. So because there is helium shortage now.
Oh,
yeah, I know that's very expensive in terms of price and power. I didn't realize, I don't have a lot of experience with superconductors.
Well, none of us did until we started MRI. And then everybody got a lot of experience really fast. Not only that, experience working in magnetic fields, which everybody has a story, right? And some of them aren't good. And the issues with the magnetic field are a perennial risk. Specifically when you roll patients into the room on a gurney. You never know what the heck's under that sheet, and so you always have to make sure everything's clean. Hence, CT is often used in ERs, MR not so much. Like in an ER, a patient can arrive, if it's trauma, with a whole bunch of devices already attached to the patient. In CT, you can just put them in, right? And just scan them, get it done. Okay. Any other quick questions on that? Sorry about the volume problem.
So
It's my fault. I'm a CS major. All computers near me.
for this course.
Yeah.
So there's team projects. So how many people are there in each team for the two projects?
We have done teams of 2, 3, and 4 before, Tom. And it sometimes, it just depends on the number of students who are in the class by the time everyone's decided to stay or go, and the amount of time we have to do the presentations, etc. That's a really great question. I don't have a quick answer. Do we know, Tom? Do we have an idea?
Once we sort of, yeah, I mean, as you said, it's going to probably be 2 or 3, and it'll determine, it would depend on, you know, how many students are in the course at the time the projects are assigned. It might actually even differ between projects 1 and 2.
Right.
But yeah, in general, it's 2 to 3.
Right. Okay. Oh, I got another question. Does some sort of reverse MRI technology exist where if you insert a magnet into a person, say for, yeah, that's a great idea. Tip of a robot. Okay, people have put MRI scanners on the tip of a catheter. And, you know, this is Christina Chan asked this, like, hey, can you put the MRI scanner into the patient, right? And so the issue is making the magnetic field big enough to get a decent MRI signal from something that's really small. So you would need a huge current density, right, down in that little small thing, that little small device. And, or you would need some kind of super material that you could magnetize. And so you have a permanent magnet in your hand and you push that in. And now you've got a permanent magnetic field inside the patient and you can structure some imaging around it. So the problem with the permanent one is that the gradient, the drop off of the field as it goes away from the little device is really steep. And so you wind up imaging in this really non-uniform magnetic field. But people have tried this a couple of times. They've tried to make MR imaging systems smaller and smaller. So don't give up. After the course, you can like do it as a project or come up with a lot of inventions and patent them, see if they work. Okay. It says people make robots that are controlled by MRI scanners field directly too. Exclamation point. That's kind of cool. I can imagine that a little robot could sense that the magnetic field is switching and the rate it's switching, and you could talk to it that way. That's a really neat idea. You could probably even combine the RF and the field gradients to you know, give that robot instructions. Okay. Okay, let's move. So we've got about 10 minutes. I'm going to go back to my presentation. First, I got to share screen again. What this? Maybe I don't want to kill that because who knows what happens if I kill it. Okay. So image quality. And we all have pretty good experience actually with image quality in the sense that like when you take pictures with your phone, you look at them and you decide, oh man, that thing's terrible, I'll just delete it. And a lot of it boils down to these issues here. And the contrast, that's pretty simple, right? It's the signal intensity of your target, the thing you're trying to look at, versus signal intensity of some background. You know, if I take a photograph of a bird in a tree, what is the signal of the bird, you know, versus all of the clutter in the background? Spatial resolution, essentially for say a camera, it's the optical resolution plus the number of pixels in the detector. For medical imaging, it's the same. What is the size of a voxel, you know, that you can reconstruct in a patient? What are the dimensions of that? How close can you get really tiny things together before they fuse into one signal? Temporal resolution on a phone is just like a blurry person when they're running, they get blurred, or if you track the person, the background gets blurred. That's fairly simple. Noise is the amount of actual signal, coherent signal that makes the object versus just the random signal that's on top of it. Can't get rid of that random signal entirely. And then you have the signal to noise ratio and the contrast to noise ratio. And we'll look at all of these things. The first thing I want you to think about is like, what is a two-dimensional signal, and you know, how it's represented on the plane. And here is a two-dimensional image. It's really a stacking of a one-dimensional image, which is the sine wave this way. And here's the equation for that image, right? It's just a single oscillating sine wave. We stack them up this way. There's no change in y, but now we've got a two-dimensional image. And a concept in imaging in terms of contrast is, if I have a sine wave that has this amplitude, I'm going to call this amplitude 1, right? What, excuse me, what does a lower contrast sine wave look like? Well, if the amplitude and the trough are 50%, or you know, the distance between them is reduced by 50%, that is a contrast of 0.5. Here is a contrast of 0.2. Here's a contrast of 0, right? You say, well, why do it with a sine wave? Well, it turns out that when we basically characterize an imaging system, we characterize its ability to transmit these oscillations, like through the imaging process. And using this type of mathematical formalism, we'll be able to see at what frequency does the imaging system, you know, fall off, or at what frequencies is it unable to transmit through the imaging process, such that if I put something in at this frequency, this is what would come out the back end of the imaging system. Like, it wouldn't get through. And that would be outside the spatial resolution of that system. And so this is just a simple definition of contrast. Here we have the sine wave going into our medical imaging system, and a sine wave that comes out. And the amount of attenuation of that amplitude gives you essentially the reduction in contrast of that frequency at that sine wave. So let's take a look at a couple of examples. This is a CT image of a phantom we had made at UCSD. I got the engineering school machine shop. These guys are really good, by the way, to drill holes in a piece of plastic. And so inside the hole is air. And so there's little X-ray attenuation inside the hole. Outside the hole is this plastic. And so there is X-ray attenuation. And we can see we can resolve all of these circles when they're this far apart and this diameter. And we keep being able to resolve them until finally, well, we're not really able to resolve them anymore, right? If you look at this image, all I've done here is I've increased the number of photons that we use to make the CT picture. And therefore, the amount of noise is reduced, and the signal to noise is higher. We can see now these smaller oscillations, these lower amplitude oscillations inside this level of noise. This level of noise is higher, this level of noise is lower. I can see these modulations, right? And you can see this, we test the limits of this scanner going down here. There's just no ability to detect these 5 circles that are down here. They're actually cylinders drilled into the plastic. Drilling really tiny cylinders is super hard. So you can make a measurement of what that contrast is by looking at a signal where they're fairly well separated, and you see the dark gray part here has a signal intensity of 100 in the CT scan, and the bright stuff in between each dark thing has a CT intensity of like 150, 160. And then as I go through that object, I see that oscillation, right? And then in the low signal to noise case, It's the same set of circles. However, the number of photons isn't enough really to make a coherent picture amongst the noise that's here. So we just basically get a mean value somewhere between 100 and 150 that's just a noisy signal, right? So it's lower image quality, lower contrast to noise. And as a definition of resolution, if we can image a dot that is, say, much smaller than the voxel that, or the inherent resolution of the system, when we image that dot, what we see usually is a blob that looks something like this in our image. It isn't a dot that is this big, because the image is not capable of making something that small. It gives us this blob. This is basically the thing that characterizes, another way of characterizing the spatial resolution of the system. If you go to the half maximum point on this function, it's called the full width at half max. And this function is called the point spread function. And that is, it's what we get when we image a really small thing. Practically speaking, if I had a ballpoint pen and I took the little metallic ball bearing out of the ballpoint pen and stuck it in a CT scanner, the diameter of that thing is way smaller than the natural resolution of the CT scanner. So it looks something like this. And the image, when it comes out, is going to look like this blob. And so I have a clean representation of what that blob looks like. That's our full width at half max of the point spread function. If I have two of those ballpoint pen tips and I bring them closer together, finally the sum of the two things looks something like that. And you can't really tell anymore that there's two of them, right? And so that's sort of how close can you put them together until it basically looks like one object. And that's called that's the way of defining spatial resolution with the Raleigh criterion. And this is also, every time that I give something like this and it's an illustration out of our textbook, I'll try and reference the page so you can go back and get their explanation, which is an alternative explanation to the concept. In contrast, like how do you define contrast? If we have a CT image and there's a signal intensity in the background, and this is our target, which say it's a disk, this is like a plot through that disk, we can define fractional contrast as the signal intensity of the target minus the signal intensity of the background. So this divided by the signal intensity of the background. And that's the fractional contrast that's sometimes used in X-ray imaging and nuclear medicine. It's a different definition than we'll see in MRI. And it's also a slightly different definition than just contrast to noise of an object in a CT image. But again, this is from Prints and Links. If we go back to the way CT images are made and look at the number of counts in our detector here versus the counts in our detector here, this makes a very sensible definition of contrast between those two objects in the raw data. And that is that. I'm going to stop sharing. Let's go back to our, so I've got the chat open. Any other questions? I know I've gone 2 minutes over, so we'll see each other on Wednesday. Ideally, please watch the lecture, lecture number 2, A and B, for Wednesday's class. And what I will do, I'll give you time at the beginning of Wednesday's class. So from 11 o'clock to 11:40, I'll sign in a little early, but to watch that lecture, and we'll start out with a little poll to figure out if people understand what happened, do some highlights, and then do some problems associated with the topic. Okay, and I'm going to stay on if anyone has more questions about today. Okay.
Hi, Professor.
Hi there.
I wanted to ask, I want to make sure I phrase my question correctly,
Sure.
but so when you draw that the square graph, right?
Mm-hmm.
So the top square, I'm trying to understand, like, I guess there's two ways of looking at it, right? The top square could be like no absorbance, right? And then
Right.
the bottom square could be like fully the highest amount of absorbance by the object.
Right.
And then the other way of looking at it is the top of the square is sort of the, like, I kind of imagine like the x-rays, or like, yeah, x-rays
Yeah.
kind of going through,
Yeah.
and it's like the number of times that the x-rays hit the detector. So
Yeah.
it would be like the opposite. It would be like the top box would be the least absorbed,
Yeah. Yeah.
and then the bottom would be the most absorbed.
So that's a very good observation, in that normally when CT images are made, or even where X-ray images are made, the physician looks at the negative. And so that means the bright signal is where more absorption has occurred. And so if we go back to look at our, say, this case here, this signal, I have plastic in the field of view. And so when X-rays pass through this part, they get absorbed. This signal is air. And so X-rays are not absorbed there. And so you get a bright signal where X-rays are absorbed, and a dark signal where X-rays are not. Now, and this is a really perceptive question, because obviously on our detector, we get more X-rays hitting the detector where there is low absorption. So out here, like if an X-ray comes through here and it doesn't hit this object at all, and it hits our detector, which is down here, we're going to see a large number of X-rays hitting the detector there. Right? So that function shows very high values where you have little absorption, and low values where you have high absorption. We'll see that function is transformed such that the polarity, where there's low values, you get lower values, and you get a negative of the scan. And I can show you, like, just on a chest X-ray, right? It comes, and the reason, I mean, one of the reasons. So for here example, in the lung field here, you can see that there is a darker signal. But actually the detector got hit by more X-rays than it did here, where the spine was in the way, and it absorbed more X-rays. And so there is a transform done on the number of counts that the detector sees in order to make this negative image, right? And same with, I think part of it is because of the history of this picture. When these images were made from here or here, right, what happened was, where the X-rays hit, you got a brighter flash in a scintillator, and that made a higher exposure on the film, and it made a negative. And so when you went and you processed the film to create the image, the greater amount of silver iodide showed a bright spot where there was a lot of X-rays, and so it naturally came up as a negative. And so that's why it looks like this. On a digital X-ray detector, if we had a digital detector behind this patient, then the digital detector would see high counts here, lower counts here. That's absolutely right. Okay. And that definition of contrast, where you have the fraction of counts at one position versus another, works particularly well when you're looking at contrast on the detector. It works less well for me when we're looking at, say, Hounsfield units on a CT image. And we'll see that when we look at some examples of contrast to noise in real images.
Okay, thank you, Professor.
Sure. Any other questions?
Hi, I was a little curious about if MRIs are used live during surgeries to kind of track things, or is there some sort of smaller, compact MRI machine that they bring into the OR?
Yeah, that's a really cool question, because in the, I want to say early 90s, say 92, something like that, 93, some crazy visionaries started building MRI scanners in which you could put a patient and then a surgeon could walk up to the patient and do surgery and then stand back and they would do an MR scan and then they'd look at the MR scan and then continue their surgery, right? That scanner had a big gap. So it was like two donuts stacked horizontally end to end, and the surgeon would walk between the donuts. One of the issues with that is that basically all of the surgical equipment that people use in a standard way doesn't work well in an MR scanner. So they had to redesign all their surgical instruments. So that took a lot of effort. And then I think the biggest problem is that MR takes time to acquire the pictures. And so you have to be willing to stand back and wait for N minutes to get the image. And then the surgeon has to ask, is this worth the N minutes that we all just spent standing around waiting for the MR? The way it's done now, most of the time, is the patient will be on an inclined surgical table, and a huge cylindrical MR machine tied to rails on the ceiling will emerge from a cupboard and go over the patient and then move back away. And then they have the updated picture.
I see.
And that company made maybe 25 of those machines or something like that, between 20 and 50, and subsequently went out of business. And I'm not sure if they're still in business. They were resurrected for a while, but I'm not sure if they still are. That's a good question.
Thank you.
Sure.
Also, another question.
Sure.
Do air bubbles show up as well in MRIs as well as X-rays? Kind of
Yeah, absolutely. So as you can imagine, in MRI, because there's very low density of material, it shows up as zero signal. And in an MRI, it will locally modify the magnetic field around the bubble. So you'll not only get zero signal inside the bubble, outside the bubble, you'll get phase shifted signal of the stuff that's around the bubble, right? Because they're resonating at slightly different frequencies depending on their orientation with respect to the bubble and the main magnetic field. That's a really cool thing. I mean, if you put a circular hole in water and then you look at the magnetic field around that sphere, it's pretty cool. In CT, bubbles show up, absolutely. They show up as little dark spheres, or whatever the shape of the bubble is. Because again, there's no X-ray absorption by the air that's in the bubble. And so it just shows up as like a hole, right? And it's something you don't want to see on an X-ray usually, because if you've injected a contrast agent and there's some kind of leak in the system, the bubbles will go in. And it's not a huge deal if those bubbles are on the right side of the circulation. So they would go into your, say, right ventricle and then out into your lungs. Yeah, it's probably okay, right? But it's not good. Not good for them to have bubbles in there.
And then just to clarify, when you say zero signal on the MRI, that means it shows up, but it's white?
That's a great question. Zero signal on an MRI usually is just black.
Okay.
Right, in the background. White usually means a very strong return of signal. So for example, if you have something with a really short T1 on a T1 weighted image, you'll get a bright signal from the tissue and it shows up as white. Now, there is no standard amplitude mapping for tissues to MRI.
Mm.
The reason is there are so many different pulse sequences, it doesn't make any sense to say, what is gray matter? It is this many MRI units. It doesn't make sense. So there's a continuous scale of intensities for all MRI. Not only that, you can have signal that has a different intensity and a different phase. Phase means they might be resonating at the same frequency, but they're 180 degrees out of phase, which is really cool. You can measure things like flow and stuff like that using the phase.
I see.
You know, and CT, as we'll see pretty soon, there is this standard signal intensity as a function of tissue.
Mm.
And if you use the same X-ray energy every time, so if your X-ray light bulb, your X-ray tube shoots out the same energy spectrum every time, you can standardize your pictures such that water is always 0 Hounsfield units, air is always minus 1,000, and everything else is governed by those 2 values that you have, sort of adjusted your scanner to tune up to.
And one more thing, has anyone ever put like an air bubble on the tip of a like surgical robotic type thing and tried to track that instead of like contrast?
Absolutely, they have. That's absolutely been done. Bubble, people have put little tiny magnets that destroy the MR signal locally. So you see a little dark thing moving around in the field of view as they move the object back and forth. We in the late 90s came up with a bunch of patents for these coils that were essentially guide wires. And so when you put the guide wire in the patient, you picked up MR signal on the guide wire and you would see this bright signal where the guide wire was, but you had to plug it into the scanner. So there's a whole bunch of ways to put signal on an object you're trying to track.
I see. And then are there air bubbles, like if they were to bring it into the OR, would they use sort of like CT type stuff instead of magnetic, like MRI stuff?
Depends. There are interventional CT suites where you have, say, a traditional fluoroscopy setup where you're doing X-rays, interventional X-rays with projection fluoroscopy. And then on occasion, you might roll the patient into a CT scanner, get a full 3D volume, and then roll them back out. And then when you're doing your fluoroscopy, you can map the CT onto that volume, right? So that's one way that it's done now. A similar thing has been done with MR, but it's kind of harder with MR. I'm always a proponent of, if you're going to introduce a contrast mechanism to see something, I like positive contrast because there's a lot of ways to kill signal, right? So you can get a lot of artifacts that destroy signal in MR, but there aren't that many ways to make signal, right? So if you make an individual, your own signal, and you put it in your own receiver, you can actually color it on the field of view and say, oh, all the red stuff is mine. That's my object. So that's one way to do it.
Okay, thank you so much.
Sure. These are great questions.